Oh, yeah. So till about then we have seen the notion of tight closure and Kuhn's theorem, and also the result of Hochster and Hunicki. So I'll try to quickly recall. So recall. So tight closure. So given an ideal in a ring R of characteristic P, which is positive, tight closure was defined to be the set of elements X in R such that Cx to the Q belong to the Frobenius power of I for all Q large and some C in R, this whatever R naught. And R naught was defined to be R minus union of minimal primes. So this is tight closure. And it was proved by Kuhn's theorem. Kuhn's. So it states that a ring R is regular if and only if f from R to R is flat. Well, yeah, one can replace this by faithfully flat, I believe. Yes, but okay. And one more result was seen, which was due to Hochster and Hunicki. It stated that let R be regular. Then for any ideal I in R, the tight closure of I is itself. So motivated by this result, the notion of weakly F regular rings was introduced. So let me state it. Definition, which is a ring R greater than 0 is called weakly F regular if every ideal is tightly closed. So till then, I think Abhiram did. And we'll try to see what else is there in weakly F regular rings. So, as a motivation, so I thought about this question and so forget about every ideals. So when is a principal ideal? When is a principal ideal tightly closed? So the reason one may think of this question is to understand every ideals, it is enough that at least we can understand principal ideals, and one can replace a principal ideal by all principal ideals, and there is some result which answers the question when all principal ideals are tightly closed. So maybe we'll look that result later, and maybe not today. So, and there is one more definition which, so one may ask this question, that why call it weakly and why not F regular? So there is a definition of a ring being F regular, which is, so a ring R is F regular if every localization of R is weakly F regular. So this is implicit in these two definitions, that the property of being weakly F regular does not commute with localization. But the examples where such anomalies arise are little difficult. So yeah, I will first state the example. So this, I forgot who gave it. So please forgive me. Or yeah, okay, it is written. So yeah, this is Brenner Monsky. And yeah, so the example is this. The ring R is, uh, where was I? Yeah, the algebraic closure of F2 and four variables x, y, z, t, and going mod of certain ideal, which is z power 4 plus x, y, z square plus x cube z plus y cube z plus tx square y square. This is the ring, and the ideal I is x to the 4, y to the 4, z to the 4. And we have to say that being weakly F regular does not localize. So the multiplicative set is this. And yeah, so the thing is F, yeah, let F be y cubed z cube. Then what happens? F belongs to the tight closure of localization, but F does not belong to the localization of tight closure. And yeah, so this example at least is enough to show that these two things are different. But yeah, there is a good result, which is state theorem. This is due to Lubeznik and Smith. Lubeznik and Smith. And this is from 1999. It states that, so a graded, and by graded it is meant positively graded, F finite. So what is this? Ring is weakly F regular if and only if it is, well, yeah, there is a notion of strongly F regular, which is not required here, but yeah, if and only if it is F regular. So the notion of being strongly F regular is a little strong than being F regular, but in this case it is equivalent. But what is F finite? So what happened? Yeah. Oh. Uh-huh. Yeah. What is coming? Yeah. So a ring R is F finite if the Frobenius map from R to R is a finite morphism. So finite morphism meaning, so R as a module over R via F is a finite R module. So for such rings, weakly F regular is F regular given that they are graded. Yeah. And so there is one lemma which is very important. So I'll state a lemma which I will prove later, but try to derive consequences from this. So let R be of characteristic P or characteristic greater than 0. Then what happens is if M belongs to the maximum spectrum of R and I is M primary, then tight closure commutes with this kind of localization. So it is I star Rm is I Rm star. And yeah, one may realize that the tight closure of, in fact, so this, yeah, this is a very trivial statement, but somehow I like this. So I star Rw is IRW star for all W. But since I is M primary, the only W for this thing is non-trivial is the complement of the maximal ideal. And yeah, so the second statement is if every M primary, so M is varying over maximal ideals. If every M primary ideal is tightly closed, then every ideal is. So I will present a proof of this lemma later. Let's try to see what all we can derive from this. So
For
the
the
first corollary, yeah,
first one, what is that multiplicative set W?
it
Like,
can be anything.
okay.
So yeah,
But we just saw that tight closure is not behaving well with localization, right?
but when the ideal is primary to a maximal ideal,
Oh, then it works for any multiplicative subset. Okay.
yes,
Oh,
and the reason is somewhat funny. So yeah, so any kind of localization can be thought of as localizing at a prime, and
okay.
the only prime at which this localization identity is something non-trivial is at the maximal ideal.
Okay. Right.
Yeah. Yeah. So yeah, that's why this second statement is not of much weightage.
So it's actually equivalent to that RM just at maximal ideal thing.
Yes.
Okay.
Yeah. And yeah, we'll prove this lemma later. So the first corollary is R is weakly F regular if and only if Rm is, for all m. So the proof is, so let's try to prove the forward direction. So, so we are given that R is weakly F regular. We have to prove Rm is. So in Rm, by the previous lemma, so if every m primary ideal is tightly closed, then every ideal is. So it's enough to prove this lemma or this direction for m primary ideals. So what we do is consider, consider and m primary ideal I in R. But then what happens is IRM is MRM primary. So by first part, it follows that this thing commutes with tight closure, which means that I is I star in RM. So IRM is I star RM. The tight closure can be put here. So RM is weakly F regular is what this shows. So the forward direction is slightly easier. So let's try to look at the converse. So once again, let I be M primary in R. So what do we have to show? That in R, every M primary ideal is tightly closed. So I take such an ideal. I have to prove it is tightly closed. But what we know is that, so I have to show that I star is I. I is trivially contained in I star. So take X in I star. But then what happens is X by 1 belong to the tight closure of I in Rm.
In the above proof, started with the M primary ideal in R, and then you got a corresponding M primary ideal in Rm, and then you proved it is tightly closed.
Yes.
So, and you are using the proposition lemma part 2 to get Rm is weakly F regular, right?
Yes.
You're trying to say every ideal is tightly closed because every M primary ideal is tightly closed, is what you are telling.
Yes.
But
So
you got the M primary ideals which are coming from the R. But how about the...
There is a correspondence. Take any M primary in Rm, contract it.
So
Okay.
I was missing the assumption that the ring is weakly F regular.
Oh, no. Oh, ring is weakly F regular. Okay.
Yeah.
That.
Right.
So
Otherwise, these things are highly non-trivial.
Oh no. Okay, that is there.
Yeah, but what he has...
His question is still valid. Like we are only proving it for M primary ideals in Rm coming from R. Like we are extending them from R. But if we are starting with any M primary ideal in Rm, is its contraction M primary in R? Yeah, contraction of primary is primary, right?
Yes.
Yeah.
Okay. Right. Okay.
Okay. All right. Yeah. Thanks.
And so now we know that. So for the converse, we know that every localization is weakly F regular, and we have to prove that the ring is also. So take a M primary ideal. We will prove that to show that the tight closure itself. So what we do is take some element in the tight closure, but its image in the localization. Yes. So Rm is tightly closed. Rm is weakly F regular. So X by 1 belongs to the tight closure of I in Rm. But what does that mean? That So C by 1 or something, yeah. Some C into x to the q belongs to IRM Frobenius power for q large. And C belongs to the whatever this thing is called for RM. But we know that since RM is, well, yeah, this is not required what I have written, please forgive me. Yeah. So, yeah, there is
I
very
think the
small.
reverse direction also follows by the same argument you gave for that.
Yes,
Going
yes,
from
that's
R.
what I realized. Yeah. So
Yeah.
this is IRM. So y into x belongs to I for some y not in M. But since I is M primary, this shows that x is in I. And yeah, so we have proved that I closure, tight closure of I is contained in I. Or equality also I can write directly. So this corollary is proved that being weakly F regular is a local property. Yes. Yes. And yeah.
Just to add to that, Kesavan's question. So the thing is actually to get the correspondence, primary ideals behave exactly like similarly like prime ideals. Like contracting and extending will get us the primary ideal we started with. You have
Yes.
a primary ideal in RM in the localization. Contract and extend, you get it back. The same one we started with.
Yes, yes. Yeah, okay. And yes, so this is done. I think I wanted to do one more corollary. Well, yeah, so let me try lemma. Well, yeah, this is nothing, but I'll still write it. Being F regular is a local property. And it is clear from the definition itself. So I will not prove it. So let us prove this lemma, which is that M primary ideals are tightly closed. Well, yeah, they commute with localization. Sorry. Proof of lemma. Yeah. So yeah, let us do first. So we have to show that I star Rm is IRM star. But yeah, it's clearly obvious that I star Rm is contained in IRM star. This is because, sorry, this is because if x belongs to say I star Rm, then Cx to the q belongs to, well, yeah, I think I have to, yeah, this is eraser. So I have to take an element from I star in Cx to the q belongs to the Frobenius power for q large. And thus the image in Rm, so which is C by 1 into x to the q by 1 belongs to I to the q Rm for q large. So this belongs to the tight closure of IRM. So x by 1 belongs to the tight closure of IRM.
Why CY1 belongs to RM not?
Yes, so well, yeah. So this is because wait. So R naught is R minus minimal primes. And so once we localize, so we only need to prove that C by 1 belongs to Rm minus minimal primes of Rm. But minimal primes of Rm is a subset of R, is subset of minimal primes of R. So whatever this thing is a larger subset. So R minus minimal primes is a smaller subset than R minus minimal primes of Rm. So in fact, C belongs to R minus whatever minimal primes of Rm. So C by 1 belongs to Rm naught. Yes, yes. So this containment is clear that I star Rm is contained in IRM star. Now we'll try to show the reverse, which is slightly, I think, involved to show that IRM star is contained in I star Rm. So, well, yeah. So what do we assume? Let alpha equal to x by y belongs to from Rm be such that I think what do I have to assume? I have to take an element from here. That is, I have to take an element alpha from IRM. Yeah, such that C alpha to the Q belongs to I to the Q Rm for all Q large, and C belongs to Rm naught. So yeah, or maybe C1 I can put. Yeah, C1. That is for use of some notation. So C1 is C by C2. And yeah. So I can fairly assume that Y is not in the maximal ideal. And yeah, thus C1 alpha to the Q belonging to I to the Q Rm gives C x to the Q belongs to I to the Q for all Q large. Well, yeah, by 1 belongs to this for all Q large. And now I have to conclude somehow that this X belongs to the tight closure of I. So for that purpose, so whenever I write this kind of P, it means a prime. PTB minimal primes of R. So one more comment which I'll say is that, so yeah, this question which was asked has helped. So we see that Rm naught is, well, I'll put in quote, larger than R naught. So this C belongs to Rm naught. And we want the element in R naught. So there is need of some tool which can give us that. So what they are doing is, so I'm trying to follow the reference book and their proof. And so yeah, so they say assume that C belongs to P1 intersection till PS, and C does not belong to Pj or j greater than equal to S plus 1. So why can they assume that? This is because the minimal primes of Rm are contained in the minimal primes of R. And therefore, since C does not belong to minimal primes of Rm, we can put them at the end, and C may belong to some of the minimal primes of R, which is the problem which we want to avoid. So yeah, so the avoidance is like this. So yeah, I'll try to say this. Avoidance is through prime avoidance. Is through prime avoidance, or the avoidance is prime. It's through prime avoidance. So we need to find, so what do we want to show? There exists D in R naught such that dx to the q belongs to I to the q for all q large. So yes. What is happening? Well, yeah. So what I had said is what I will try to write in words. So since C belongs to Rm naught, those Pi's cannot be contained in M. Because otherwise, C will be contained in a minimal prime of Rm, which is not possible. So which Pi's? I equal to 1 to S. And thus, so choose D in those. So which is contained in this intersection. So the minimal primes of Rm, and which is not in those minimal. So it is not contained in P1 to PS, but is contained in minimal primes of Rm. So such a D is a problem in the ring Rm, but it will help. So D is nilpotent in Rm. But this is because D is contained in every minimal prime of Rm, and every minimal prime is nilpotent. So that means there exists n fixed such that D to the n is 0. Well, 0 in Rm and yeah. So the proof goes like this. Suppose let I is generated by f1 till fr, then since cx to the q by 1 belongs to I to the q Rm, we have this relation cx to the q by 1 is summation aiq by biq fi to the q. I ranges from 1 to r. And yeah, and all these things will depend on q, aiq and biq. So what we do is let E to be C plus D to the n. Then E by 1 is C by 1 in Rm. And E belongs to R naught. This is because since C is not contained in some minimal primes and D is contained in those minimal primes, these things, so I'll try to say that C does not belong to minimal prime of Rm. But D belongs to those minimal primes. So C plus D cannot belong to a minimal prime of Rm. But C does not belong to minimal prime of R minus Rm. But D, yeah, C belongs to such, sorry. And then D does not belong to such minimal primes. So C plus D to the n cannot belong to those minimal primes. So this sum C plus D to the n cannot belong to any minimal prime. Therefore, this sum E is in R naught. And also C by 1 is E by 1 because D to the n is 0. Yeah. But yeah, so what we do is, so we clear the fractions. So this relation, suppose 1 gives yeah, let B to be product BIQ, then B E x to the q by 1 lies in I to the q. Because we have cleared the denominator. Oh yeah, I have to remove by 1. Yeah. But since I is M primary, I to the q is also M primary, and B does not belong to M. So this implies E x to the q lies in I to the q. And yeah, so this is what we wanted. This proves that X belongs to the tight closure of I. So I'll try to recall the proof once again so that I remember it. So it is like this. Yeah, so this we have to prove that the tight closure of a M primary ideal commutes with localization. But this containment I star Rm being contained in the tight closure of IRM is clear due to some argument about minimal primes of R and Rm. But now we want to show the reverse inclusion, which is the tight closure of IRM is contained in I star Rm. So for that, let alpha be x by y in IRM such that alpha belongs to the tight closure of IRM. So basically, element from the LHS. Then this C1 alpha to the Q being
I think
in
you're starting with an element in RM, right? Or IRM?
IRM. Oh, sorry, I am wrong. Yeah, thank you. Yeah. So this is in RM, which is in the tight closure. Yeah, thanks a lot. So such that C1 alpha to the Q lies in the Frobenius power of I. And we assume C1 is C by C2, etc. Then we can multiply denominators to get a relation like this. C x to the Q lies in the Frobenius power of IRM. But if C were in R naught, then this thing would have been clear. We could have directly concluded that X lies in the tight closure of I. So suppose that thing is not happening and that C lies in some minimal primes, P1 to PS. They can surely not be minimal primes of Rm because C belongs to Rm naught. And so we want a D such that dx to the Q lies in the Frobenius power. So what we do is we choose a D. Well, yeah, then we want a E is what I should write. Because we get an E. We choose D such that it lies in precisely those minimal primes in which C does not lie. So that the sum C plus D or C plus D to the n cannot lie in any minimal prime. So using that trick, we are able to deduce that X lies in the tight closure. So the first part is done. Now let's try to do the second part of the lemma, which states that if every M primary ideal is tightly closed, then every ideal is. So there is one trick which we can use. So it is I is either so I has this representation, but each of these ideals is either R or M primary. So if I is contained in a maximal ideal, this is M primary, and if not, this is R. Yes.
Is this just Krull intersection theorem or?
Yeah, this is
on R mod I?
Well, yeah, true. On R mod I, yeah. Yeah. So I can write like the same of R mod I. And yeah, so what we get is I star, which is the tight closure of this thing. So this is one result which maybe I will not prove or prove, I don't know. So the tight closure of this intersection is contained in the intersection of tight closure. But each of these things is M primary, so this is itself. But this is I. So I star is contained in I, which gives I star is I. Yes. Yeah,
If it is,
so
if it is Krull intersection theorem for R mod I,
yes.
it's not a local ring, right? So you must be multiplying with the some element along with the intersection to make sure it is I again, right?
Well, yeah, what is being done is we are taking all maximal ideals in R mod I, which is giving us. So just to reiterate, so what we can do it, localize at complement of M spec R mod I. Yeah, will that work?
Yeah, I'm not sure because we are taking all maximal ideals, not those containing I. So
yeah, that's not
there is
true.
that. Yeah, there is some issue.
But still, so we can take finitely many maximal ideals, which are the primary components of primary components, right? Which are maximal. That's not true. So yeah, there has to be. So okay, this is clear.
Oh no, see, I is M primary, right? Here you assume.
Well, I am not assuming that.
Oh, okay.
So we have to prove that if every M primary ideal is tightly closed, then every ideal is. So
Oh, okay.
So what actually we can observe is, suppose I localize the right hand side at any maximal ideal, it is I. It is I localized at it. So both of these things agree at every localization, therefore they agree everywhere.
So why is the right hand side I when you're localizing it every maximal ideal? Actually, this
Yeah,
set is not finite, right? This intersection.
no, it is not.
Oh, it's
I think if we localize at a maximal ideal, then it will be the Krull intersection for
Yes,
RM mod IM, I guess.
yes. But yeah, that is clear, no?
Okay, yeah.
Yeah, okay. Okay, so we have proved this result. And I'll state one theorem.
Can you just scroll above like for a second?
Yes.
A couple of.
Can I zoom out? Yes.
All right, okay.
Yeah. So this is one property of weakly F regular rings. So weakly F regular is a domain, first of all. In fact, it is a normal domain. But this property is something very nice. And yeah, I think it's 954. And yeah, this may take some time. So we can discuss the tutorial. Was it done by Abhiram?
I have a general question. Like, actually, I don't know much anything about integral closure. So here for tight closure, we are trying to characterize rings whose ideals are tightly closed, right? Do we have
Yes.
any such notions for integral closure? Like, continuing with the analogy we have of tight closure and integral closure.
I think that is called normal.
Okay. Oh, so normal rings are, all ideals are integrally closed.
Yeah, I mean that I'll check. I'm checking
I am
just
not
now.
sure. Oh, so we have a characterization like that for integral closure.
I think normal domain means it will be integrally closed in its field of action.
Oh yeah, that is the notion. I'm sorry. Oh, but yeah, normal rings are not like that, in which every ideal is closed. That does not follow.
Yeah, I just googled even. I think only principal ideals it's telling for normal rings.
Yeah,
Only
and yeah, okay. So this is the answer to that question, which was
yeah. We can relate because we already have for principal ideals tight closure as same as integral closure, right?
yeah. So if every principal ideal is tightly closed, then the ring is normal. And think image of Cohen-Macaulay or something.
Oh, there's more you can tell. Okay.
Yeah, so there is one notion where when rings are homomorphic image of Cohen-Macaulay rings, but yeah, I am also not very comfortable with that notion. I will read it and understand. But it is used in these notes is what I saw.
So by the way, for integral closure, there is no such notion like all ideals are integrally closed. Right?
Wait,
So
I will try to Google.
I only got this. I mean, for principal ideals, like when I was Googling it.
Oh, then maybe people have not studied.
Maybe it's too much of a strong condition or too weak. I'm not like, is it that issue? Like if it is too strong a requirement, we won't have a classification. There won't be a big family.
Yeah, but it's not there in Hunike Swanson, no?
I don't know. I'll check there.
Okay, yeah. Hunike Swanson. Integral closure. Search every ideal. So how many occurrences of every ideal? Yeah, okay, anyway. Let's try to see the index. Dedekind Morton's formula. Wait, I'll share screen for this only. Entire screen. Yeah. This is visible, no? Yeah, maybe we can stop recording also.
Yeah, I'll stop it.
Okay, thank you.